So welcome. Welcome to our talk, Build and Test AI Models for Trust. My name is Mayuk Bhawal. I'm a product management director at Salesforce Einstein. I work on our automated machine learning and data science experience initiatives.
My name is Tol Bergman. I'm a senior data scientist also at Salesforce Einstein, where I also work on automating machine learning.
Awesome. So today, we are here to share our experiences building large-scale, real-world machine learning applications. And one of the specific challenges we faced in the process around building trust and making your machine learning models more transparent. So that's what we want to talk about. So let's get started. Well, of course, we have our forward-looking statement. Our lawyers wants to say something to you. And you might have already summarized this slide by now, but just to boil it down, don't buy Salesforce stocks just based upon this session, okay? So with that said, let's really get started. In this session, we're going to talk about what model explainability is, why do you need to explain your models and why now, the 3 trade-offs that you have to consider while building trust in your machine learning applications, and last but not the least, the power of a naive solution. So, what is model explainability? So you all know Salesforce is an enterprise company. We build software in many different verticals, such as sales, marketing, commerce. For instance, US Bank is a Fortune 500 company, and we work very closely with their wealth management division. You see, they have 16.9 million retail customers, and they're trying to figure out which of those 16.9 million customers are going to resonate well with their wealth management value proposition. So we built a predictive application for them. Another use case that they have is of the existing wealth management customers, how many of those are about to churn so that they can act on them and retain them. So it's not hard to imagine, just like US Bank, we have many other enterprise customers and many other use cases. What's interesting, though, is many of them are experiencing predictive applications in the enterprise space for the first time. And naturally, there have been a lot of questions that have popped up in many different directions. And as we are talking to our customers, to you all, one of the most common questions that we have heard is, why did the machine learning model make the decision that it did? It might feel like a seemingly innocent question, but as we peel the layers of the onion and dig deeper, we find that based upon who is asking, it has a very different meaning. If a data scientist is asking the question, she is interested in her ability to debug the machine learning model. If it's a legal officer or a compliance officer who's asking the question, he wants to know if the company and their people are protected in case of a regulatory audit. If it's a non-technical end user who's asking the question, they really want to know that does Einstein really know what they know? Like, they have all these years of experience and years of intuition. Does Einstein has all of those information? So, model explainability is answering that singular question. And it's a lot trickier than you would think, because machine learning software differs from traditional software in the sense that the outcome is not based on a set of hand-coded rules, and therefore it's not very easily predictable. What's happening is the behavior of the software, it's a learning software, so it changes over time based upon data and feedback loop. So the model becomes more and more like a black box. As machine learning pervades every software vertical and is increasingly used to automate decision-making, model explainability, therefore, is becoming an integral part of the machine learning pipeline and can no longer be an afterthought. In the real world, what we have seen, the demand to be able to explain models is rapidly gaining on model evaluation metrics such as accuracy.
So now that we know what model explainability is, let's look at some reasons why we need to explain your model in more detail. So for me, as a data scientist, one of the main reasons is really that I want to be able to debug my model for myself and explain it to myself, basically. So let's say we run a model and we try to predict whether a customer is going to purchase a product or not. And in our offline training, this model does really well and this has a high accuracy at actually giving the correct prediction. But then we roll it out to production, and after some time, we can run some evaluation on this model to check, well, out of all the things that we predicted, how many of them were actually true in the long run. And we discovered that our accuracy actually dropped significantly, as you can see in this plot. And now what we can do is we can look at these top contributing features, the features that really explain why the model is doing the way it is, and that really drives the prediction. And you can see that the first one, customer interest group, and the third one, customer location, are both about the customer and kind of like make intuitively sense that they would drive whether you purchase a product or not. The second one, however, the thank you email, is a little bit suspicious because usually you only get a thank you email after you purchase the product. You don't get it before you make the decision, and you definitely don't get a thank you email if you decide not to purchase the product. So this is something that we call it label leakage, and that we only really discover when we run something in production and can evaluate it on real life data. We can't really catch this in offline training. But here I'm able to kind of like explain why this model behaved badly, and we can do some actions to correct that in the future. Another reason is bias. So machine learning software is trained on some data, and this data is produced by some humans in some kind of form. And there's always some bias when humans are involved. So even though machine learning is all about math and formulas, this bias gets picked up. So here, this is a Google Translate example. On the left-hand side, you see some sentences in Turkish, a gender-neutral language. And on the right-hand side, you see the translation into English. And you can see at the beginning, at the couple of sentences, that this is kind of problematic. So you see that he is a soldier, but she's a teacher. He is a doctor, but she is a nurse. And to make it even more extreme, it also can result in things such as he is hardworking, but she is lazy. And again, to iterate, in the original Turkish, no such distinction was being made. It doesn't talk at all about he or she. But because there's bias in the data that we provided machine learning with, it picks up this bias, and to make it worse, it even exacerbates it because it's really good at picking it up. A third rationale is legal. Some industries, such as healthcare and banking, they're really highly regulated by law, and you have to be able to provide explanations. For example, if you go online and you check your credit score, you can see that there's multiple reasons listed, both negative and positive, on why the score is as high or as low as it is. And that's simply because it is required by law that the banks have to give you a reason. In some markets, such as Europe, there's really broad regulations now, such as GDPR, which have a notion of right to explanation, which means that any decision that has some kind of machine learning involved in it needs to be explainable if a customer demands an explanation. And like we've just seen with the bias example, those are all really, really important regulations. And just to kind of like iterate this home, here's another example. So some states, such as Wisconsin, they now use third-party software that is based on machine learning to assess whether a defendant is at risk of committing another crime in the future. So in this case, a man committed 2 minor crimes that didn't mandate any prison time. And however, based on this risk assessment algorithm, the judge decided to sentence this man to prison for 11 years. Now, if you're in that position, you would want to know, why am I being sentenced to prison? Like, what are the reasons that kind of like play a role in this machine learning algorithm, this black box that decides about my life? And here we're no longer deciding, is this customer going to purchase a product or not? It's really like a life-changing decision that is being made by some kind of software. And to make things worse, again, because this machine learning algorithm is based on data, this data is biased. And it turns out that these risk scores that this machine learning algorithm has were highly biased against black defendants. So on average, they were much, much higher for black defendants than they were for white defendants, with all other things being equal.
I love some of those examples around bias and legal reasons and debuggability, why we need to make our machine learning models more explainable. Here is yet another reason why this is more and more important. As we build out Einstein and we surface predictions and scores to our users, they want more out of it. They want insights into those scores so that they can act upon it. So we need to make our models more actionable. So here's an example of lead score, which is the likelihood or the propensity of a lead converting into an opportunity. And what you see here, we are surfacing insights like the top factors which are responsible for your lead converting into an opportunity. So let's zoom in factor number 3, which says downloading a white paper. This is based upon the correlation that incoming leads who download more and more white papers are more likely to convert into an opportunity. Now, this is great, and the first intuition as a result of this is, let's go and optimize my website, do whatever I can do to make sure my incoming leads downloads more and more white paper, with the hope that that would help increase sales. But I want to throw a word of caution here that this is merely based upon correlation, and correlation does not imply causation. However, you can still make it actionable. You can devise a meaningful hypothesis that downloading a white paper indeed helps with a higher conversion. And then you can devise something like an A/B test, where you test version A versus version B, which is downloading a white paper versus your default CTA, and prove if there is indeed a causal relationship between downloading a white paper and you having a higher conversion. And finally, our favorite reason, and it's no surprise, it's the title of this talk, it's trust. Trust, however, is an extremely nuanced concept. Like, you can define it in so many different ways. Someone might define that trust is about machine learning accuracy, how many times a machine is right versus wrong. If it is that easy, there is plenty of metrics today available to be able to make that decision. However, some of you might define trust as the steps that the machine learning algorithm takes in reaching its final conclusion. It turns out that the second definition has much more weight because it makes the machine learning application less scary and less intimidating. So we as humans are interested not only the percentage raw numbers, we are interested in the scenarios and the examples where the machine is right versus wrong. For example, if in the areas of the input space where the humans are right, the machine is also right, and in the areas of the input space where the humans are wrong, the machine is wrong, it can be argued that the model is trustworthy. And the reason being, there is no apparent cost of relinquishing control to the machine learning model. However, on the contrary, if in the areas of the input space where humans are right, you guessed it, if the machine starts making a mistake, we can say that the model is not trustworthy, because I would be very worried in giving control to the machine learning application, and I would like to continue supervision over that machine learning algorithm.
So now that we know what the reasons are behind or need to explain our model, let's move to the solution space and cover some trade-offs that we had to deal with when we were trying to solve this problem. So sometimes the explainability of a model is really at odds with the accuracy of the model. Sometimes the explanations that you want to give the customer are of global natures and sometimes only of local nature. They can also be aware of the model or completely model agnostic. And I will go through all of these three trade-offs now in detail. So the first one is very straightforward. Some models, such as linear regression decision trees, are relatively easy to explain. You get some mathematical formula at the end where you can immediately deduce this feature is twice as important as this other feature. However, the accuracy at actually predicting something is not always that great, compared to things such as neural networks, which are really popular now in deep learning, or support vector machines, which might give you better accuracy at whatever you're trying to predict, but they don't give you like a nice mathematical formula at the end. They're a little bit more black boxy. It's not that easy to actually explain why this model made the prediction that it did. This is also true for the feature space, for the input that we feed in. We usually transform these into like some other features to get a better model. Here in this example, we're representing the word overfitting with different representations. And the first one is really straightforward, which is what we call a unigram, where we just split up the word into individual characters. So overfitting becomes O, V, E, R, and so on. We can also do some more advanced methods, such as TF-IDF, where we weigh the occurrence of the word basically against all the occurrences of all the other words, and you get some kind of weight score, such as 0.13. Now, if I tell you, just looking at this, obviously a character like O is much more humanly understandable than some score 0.13. Even more advanced methods, such as word embedding, result not only in one number, they result in a whole vector of words. And if I go to the customer and tell them, you know, your model performed this way because the second index of the word vector is 0.34, you don't really know anything more than you did before I told you that.
The next important trade-off that you have to consider while building explainability is global versus local explanations. So if you're trying to explain your model as a whole across the entire data set, across all the predictions, it's known as a global explanation. Whereas, on the contrary, if you're trying to explain a single prediction, it's known as local explanation. I'll give an example. Imagine a sentiment analysis model. If I have to explain a sentiment analysis model, I have to explain to you you have to understand the huge size of human vocabulary, the context of the words, the complexity of negation. Whereas on the contrary, if I have to explain why a single sentence, this is not bad, has a positive sentiment, it's much easier. To drive this point home, I'm going to use an example of housing prediction, the price prediction, which is very common in Zillow and Redfin and websites like that. I've used a much more simplistic example. We have 4 features here. The square footage of the house, which is x1, the number of bedrooms of the house, the number of floors in the house, and the age of the house. And what we are trying to predict is the price of the house, the variable y. Now, a data scientist would fit this into something called a linear regression equation. Don't worry, you don't have to understand anything about how that features and the values got fit into that equation. That's not the point. What I'm trying to highlight here is the coefficients for each of those features. In this example, x3, which is the number of floors of the house, has the highest coefficient of +3, and x4, which is the age of the house, has the lowest of -2. So if I have to explain this model globally to you, I would say the more the number of floors the house has, the more expensive it is, and the older the house is, the cheaper it gets. So that's an example of a global explanation. So what is the local explanation? If I have to explain to you why the price of that single house is $178,000, now we are talking about local explanation. And here we can fill in the actual values that we have, and it turns out in this example, the square footage of the house has the most important factor driving that price and not the number of floors of the house. So this is a trade-off you need to think about. So if you're an admin and you're rolling out Einstein to a bunch of your customers, you might be more interested in global explanation because you want to understand how the model is performing as a whole. But your end users, they don't see other people's prediction. They just see their own predictions. So they need to see more local explanations.
The third trade-off that we had to take into consideration was whether you want your explanations to be model-aware or model-agnostic. So like we mentioned earlier, some models are very, very good at giving you highly accurate predictions, but they are a little bit more black boxy and are a little harder to explain what actually happens under the hood. But you might still want to use such models to really give you the best prediction that you can. And in such a scenario, you can train a secondary model that is easier to explain, such as a decision tree, to provide the customer with the explanation. So here you can use a decision tree, and you can say things like, this customer lives in California, so they are more likely to purchase the product. Or you can even use completely model-agnostic explanations, such as correlations, where you can say things such as, the older the house, the less expensive it is. And that is very easily understandable to anyone. Now you might say, isn't that a little bit like comparing a teddy bear to a grizzly bear? And yes, that's true. You might not actually, these easy explanations, the teddy bear explanations, might not always actually explain what happens under the hood of the more complex model super accurately. And this is especially the case the more complex your data is. For example, if you have interactions between different features and all of these things that are going on in the black box model. However, sometimes people don't really want to see the grizzly bear, they just want to see the teddy bear.
Hey, I'm scared of grizzly bears. I think all of our customers would love teddy bears, so I think we're doing a pretty good job there. All right, so, and the final part I want to talk about is the power of a naive solution. So, as we started down this path of trying many different technologies and many different ways to be able to explain our models, we realized that you don't always have to come up with the most sophisticated method. In reality, what we saw that you can meet 80% of your customer needs with a very naive solution. For instance, if you even know the most important factor, just one factor, that's affecting your model, you can turn it into a plain English sentence like so. The source of this lead is an inbound call, and leads with an inbound call are more likely to convert. You can take this a step further with the lead scoring example I showed earlier, so you can show the top positive as well as the top negative factors. Now you're giving more transparency into your machine learning model. You can also show suggested actions. In this example, it's a churn probability, and it shows that customers who are monthly and tenure who is 18 are more likely to churn. And therefore, the suggested action is, why don't you upgrade them to a yearly contract? And what I want to highlight is these techniques work even in deep learning algorithms, such as image classification. So here's an example of a machine learning system taking an image of a cat and saying it's a cat because it has fur, whiskers, and claws. Now, you all know what a cat is. You have all seen that. You have that experience. You have that intuition. And you know those insights are true. So once that happens, this magical thing is happening. The machine learning system is addressing your confirmation bias, and the system from being a black box, suddenly you start trusting it because there is some transparency and it's confirming what you already know. So I want to end this talk with a very simple message. No matter how sophisticated machine learning algorithms you use, or how cool your demos are, or how successful your pilot program is, lack of trust is likely going to be a barrier for general adoption of your machine learning software. What we have seen in real world as machine learning is eating software, the demand to be able to explain models is rapidly gaining over accuracy and other evaluation metrics. With that, thank you so much. Oh, I forgot one thing. So all of these things are available as a part of our automated machine learning library called Transmogrify, which we recently open sourced last month. So if you have a chance, go to Transmogrify, check it out, and do not forget to star us on our GitHub repo. So really appreciate it. With that, thank you so much. Thanks for joining. Give yourself again a big round of applause. Thank you, everyone. If you have questions, we are right down there.